Thank you. My name is Ewald Jacobi. I'm head of economic information analytics in Germany for Deutsche Bank. And in that context, I'm providing him a realistic case example. It's still basic, but it's realistic to give you a flavor and give you a view into the machine room of data analytics. Because I've served at various conferences in the past that most times we talk about data analytics and big data and stuff like that. And the part between data preparation and data interpretation we do not unveil. So this is becoming a black box. And this issue is becoming even more prominent as we start to apply deep learning on neural networks, because they particularly do not unveil their secret. And for that reason, I'll present you here an approach which gives more control of what's happening when you analyze data. And this particularly has the favor, and that's why we had chosen to apply that in that context, is because we could look into the box, identify root causes for something which happens in the data or which happens to which we do see in the observation, and then tweak that to account for intuition or better knowledge aside historic data. And that's where I start. And this is a case example from talent recruiting, but you can easily substitute that to any other problem. But this was of interest at the end of last year for us, and we solved it via a very basic but insightful approach. So the strategic aim in that context was that in talent recruiting we were questioning what is successful talent recruiting, and for that purpose we were looking for the most promising intake channel. If you think of talent recruiting, you see people coming from external via executive search, internal hires, temporaries, change to permanent, and so on. But being agnostic of the original foundation or of the original problem, we've applied this approach for other insight exercises we did and was successful as well. But as I'm HR, as I said in the beginning, we have several of these problems. So what is a good prediction from your point of view? A good prediction is founding on reliable statistic. That means you have some robust data in terms of you can go forward in the data 2 quarters, 3 quarters, 1 year, or you go 1 year back in the data, or you change from region to region, and at least what's happening between the data is not something irregular, so you can understand why this data is in such form as it is. So it's to be reliable statistic, you have some substantial knowledge on the historic patterns. But that's not all. From my point of view, and this is the thing which I will share 2 war stories, why this is important, a pure mathematical handling of this is insufficient. We had various vendor discussions last week with people with external vendors which we provided toy examples, and they should give us analysis on this toy examples and tell us what will happen in the future. And what they normally did was simply they extrapolated the data at best case. In the worst case, they simply took averages of the data. But in the best case, they did extrapolation. But this lacks your expertise in these regards, and therefore understanding and intuition is viable for explaining from data as of today into the future. Doing a good prediction is required to have your expertise embedded. And I promised 2 war stories to share with you. The one war story was in the bank when we approached a strong restructuring phase, and we were discussing the flight risk. That is the risk of people getting off the platform for voluntary reason. And this is a phased transition in that regard. So something is fundamentally changing in your system which has not been before in that system, and you need to proactively react onto that 6 months, 12 months before, and by that you need to understand what you have observed in the past and tweak and tailor that to the things you anticipate to happen. And with regards to this restructuring phase the bank has entered, we made tweaks into the flight risk predictions, and by that reason we're even more successful in predicting that flight risk. The other war story I can share is not from me, but is from the energy sector, from Franck Mastieu, who's currently CEO of ENBW. He shared that at a networking event last year. When he was responsible for the renewable sections at E.ON, which is a large energy provider in Germany, they decided if they should enter the solar production market. So they made dozens of business cases if it was valuable and promising to create own solar cell production facilities. And he said most of the business cases were on tilt, so some were in favor of these entrance of these new businesses, and some were against that. And just some months before the decision, one of the involved managers in that project had a flight over China, and looking out of the window, he saw half a dozen of solar cell production facilities being built up. So these facilities were up and running 1 or 2 years from that on, and he was expecting from that observation, which was not in the data, which was not in the business cases, that the price for solar cell would fall dramatically, and by that they decided not to involve in the solar cell production. So this is a second example where expertise, intuition, or other things which are not in the data have made substantial and successful business decision making. And this is important when handling data, because it's for most people using data, it's kind of a black box. There's data entering, then this is facilitated and processed by neural networks, sophisticated methods, random forest techniques, and so on. And then a result comes out, and reading the table gives you an interpretation. But that doesn't relieve you from making your own assumption on that, and as one of the lecturers before said, making your common sense analysis or on that what you see and what you derive from your data analytics. So what I will here present is a basic example for getting into the machine into that black box and making your own data analytics, and that can be even done with an Excel sheet, so it's not too complicated. So with regards to this problem, and the method completely is agnostic of the problem itself, you have some key performance identity indicator which you want to predict. This is typically something, as I said, market risk, length of tenure, or in market sense would be sales, revenue, or what else. It's agnostic of that. And then you would identify, and that's what we will do on the next slides, the relevant dependencies in your data, which are root causes which drive this key performance indicator. And now it comes into the black box. We apply in linear model ansatz. This can be done via Excel, or you could even do that on a sheet of paper. Calculate the coefficients of that model. That's straightforward. That's basic mathematics from university. Then you can do some backtesting just to ensure you've done the right things. And then you can, as the model is simple, factor in your prediction or your better guess. So has some of you ever heard of an ANOVA test, of an F-test? Okay, that's good. Some of you ever applied such one? Okay, that's perfect. So essentially, it's quite simple. You do have some data points lying somewhere in the field, and you just want to know if these data points, if this cloud of data points can be differentiated by a certain attribute. So in that example, it's simply two colors which have the data points that can be female or male, for example, and you you simply ask, does that make a difference if I am female or male in that example? And then the ANOVA test simply calculates the probability of the underlying distributions of these two kind, in that example, of these two kind of sets is different, or is it less probable that it's different? In the example I'm showing here, which is talent recruiting, we've had identified just 4 dimensions of being relevant, and that relieves you of a lot of data which is simply waste in your problem and which you do not take into account for. And so you have your tons of data reduced to the minimum set, which makes it even more simple to interpret and to process. And what you see from the top to down, so recruitment source obviously is some kind of important for that example. There's some regional impact, so country is important, division, corporate title, and in that realistic and example, senior management was quite relieved that gender and age were not important for the recruitment sources in terms of success of recruiting. So having that, we know what the fundamental dependencies of our key performance indicator are, and now we're developing a linear model. So we simply determine the KPI as a function of the major relevant dimensions we have identified. This is a functional approach, which is simple, and we now do the modeling assumption. The modeling assumption in this thing is that we have a product of things. This can also be a sum. I can tell you later why we've chosen to make a product here. So there's some factor which accounts for the recruitment source, some factor which accounts for the country, some factor which accounts for corporate title division, and some factor which accounts for the year where I have made this observation of the certain data point in my whole data set. Then I'm doing some simple mathematics, and this is now here taking a logarithm of that formula, and this is just because of the approach in the first line. This is a product which I cannot make a straightforward linear regression to, so I'm taking the logarithms of this equation, and by that unveiling sums of influencing factors. And if you recall your first time, or your time in school, or your first time at the university, now this is becoming a linear equation being dependent on your 4 or 5 central factors, and this linear equation can be then solved by a linear regression. For most of the problems you have, these factors are not simple in terms of they are some linear dependency, so it's not depending linear on the revenue, for example, but they're depending categorically from a variable such as the country. So if you have Germany, United Kingdom, France, Spain, this is not something you can put an order to, this is just different. So these factors will have an influence, but then you cannot order them. And so what you're typically doing is so-called one-hot encoding. So this makes out of one factor just a sum of 6, 5, or dozens other factors. So essentially now you're done with the model. So you have created a model where you have on the left a predictor for that model length of servers, or for your KPI, which depends on a sum of 40 other factors. And these factors are not yet determined, but you can easily do that with Excel sheet or R or SPSS or what else. And by that, determine exactly how these factor, which value of these factor have. And what you here see is from left to right, the value of the different factors. This is sanitized data, so this is not exact. But you see that on the very left, you have some amplifying attributes. So the better the employee is known before, the longer the length of servers. So which was the KPI which was of interest for us. The same holds true, for example, for the corporate title structure. The higher the corporate title, the longer the length of service, which was the KPI for us. So for example, if you have revenue, if you make a revenue prediction, then you would be interested in the insight, the higher the price, or the higher price the product, the higher the revenue, for example, or you have some opposite behavior, which is in agreement with your intuition. So data analytics possibly is in agreement with your intuition, which is a good sign that you have made the right things. But you now, and that's essential, you now can disentangle all of the different factors. And this is something which is not easily possible when you use a neural network, for example. A neural network directly combines all the attributes entering in the example or in the sample, combines them, and if you have a look on the neural network, it's blinking and twinkling and things like that, and in the end you get the result for each of the samples you have entered. But it's extremely difficult to disentangle the different factors which you would then qualify in the aftermath. And this is a simple method where you can disentangle the root causes for your outcome, you can qualify them, and this gives you an extremely robust situation when you have senior management discussions, for example, who in most cases have some do gain trust if they understand what's happening in detail in your models. And this is even more easy if it's not just a black box. So if we have developed the ansatz, we have determined the coefficients for the model, and now we are simply backtesting. So we check, does the model yield what we have introduced in the model? Because the original data set had about 5,000 samples, so 5,000 data sets, and we now have reduced that data set to the essential 45 coefficients. So we now are describing 45 samples with 5,000 samples with 45 coefficients. So we've drastically reduced the information, but we have understandable information, and it's now very simple. And this, for example, gives us the opportunity to see if these 45 correctly describe the whole data set and what are the differences, where the differences lie. We have also statistical uncertainties which cannot be factored in such a simple model. But we have some quite good agreement between the model prediction and the data itself. So here 3 case examples are taken, and you do see if you compare the length of service as the key performance indicator by model and by reality, that they resemble. So, and now comes the final part, the predictive part. So we've essentially had identified 5 dimensions of interest. The 4 dimensions we've qualified on the slide before, and the last was the temporal thing. So what happens if we are today? What happens next year? Can we learn something from the past? And you now see the beauty of this approach because you can easily tweak the approach in that and factor in your prediction or your intuition into the problem. You see we have the factors for the previous years, and they do have some decline. The question is what happens in the year after, 2016. This was the original question, and we've chosen to make a very linear regression. This is not in the data themselves. So a neural network, for example, wouldn't have told us what will happen in 2016. You need to factor that in. And so we've made an extrapolation for that, and we're able to tweak the model in that way, put a completely new data set into this model, and derive a prediction based on historic data, but also on the intuition expertise we had as well. So that's it. So coming to the conclusion, and I'm looking forward to your questions afterwards. So the benefits of simplistic models is it's very easy to understand and to interpret. So this is nothing. You can argue what happens if we do something different. What happens in UK and in Germany? What's the qualitative difference between these two regions? Does it boil down to a single number, for example? And it's very easy to tweak and tailor that to your intuition to make the models which have learned from the past adapting to future problems. As I said, and that was the point where we started, the disentangling of dimensions from my point of view absolutely essential to understand data. So there's in data you have complex interference between different parts of that data, and you need to make an approach to disentangle that at its best. That won't be possible in general, but the better you do, the more easier it is to interpret the data. As I said, it's a realistic case example. So 5 steps or 6 steps I have provided. So identify the right key performance indicator, identify the relevant dependencies, develop some simple model, calculate the relevant coefficients, which can be done via an Excel if it's simple enough. Check the validity of your prediction or model, and then you can insert the intuition, the predictive part, not doing something general, but doing that surgically at the right point in your model and injecting your information. And but this is common sense. Afterwards, check what comes out, if that at least matches your expectation. If not, you should take another step, another round. Okay, thank you.
Thank you. Ed Hart, we again have a lot of questions in the Slido, but I'll just try and bring one together as a little bit of a summary. There are a few questions around, there are lots of different types of regression, there are different models, discriminant, structural equation, etc. Why and how did you choose a linear regression? And do you look at all sorts of different models when you're considering answering these kind of questions?
Yeah, particularly this approach, when we first did that, we made benchmarking against also neural networks, for example. And they weren't that superior compared to that simple approach. So in the end we chose to stick to the simple approach because, as I said, transparency was critical for that decision. And in particular, strategy decisions typically do not benefit from a 2 or 3 percentage points precision. If you do a strategy decision, this typically has plus 30% or minus 20%. And so it doesn't matter if your model is extremely precise or just precise enough. And if the latter has the benefit of being easy to understand, transparent, and easy to communicate, then I would always favor a more simple approach instead of a technically extremely advanced approach.
That's great and reassuring to hear. Thank you very much.
Thank you.